So thanks for the invitation. This is a very specific topic, universal statistics, but a very wide range of speakers. So this is, well, I'll explain how what I'm talking about comes in to universal statistics. I should say, whereas James had one piece of paper written on 2 sides for his talk, I have 100 slides, so they're different talks. So I'm going to talk about multiplicative functions. Many of you know them very well. Some of you don't know them very much. So let me just do something very brief and introduce them. And I'm going to introduce them from the sort of perspective that I've long worked from, which isn't necessarily the sorts of things that Adam and others have done in random multiplicative functions. So of course, they're certainly Adam's very aware of this sort of thing. So we take a multiplicative function, and for simplicity, we'll just assume it's always fmn is fmfn. We have a Dirichlet series. We'll take logarithmic derivatives so that we have something that pretends to be, well, it is what it is on primes, sort of suitably weighted. So it's a bit like zeta prime over zeta. And then the typical assumption we're going to make is that these lambda fn's, so something at prime powers, is bounded by k times what happens at, well, if it's p to the k, k times log p. Sorry, no, I mean n is p to the e, then it's less than k times log p. So I guess I need to use this pointer. So the easiest examples are just dkn, d minus kn, the kth divisor functions. And what I want to do is damn you, you're right. Let's not worry too much about that. I mean, everything I'm going to say is correct, and whether it's totally multiplicative or not, but yeah, you're right. So we're actually going to more or less, well, we're going to take some sort of average of what happens on the primes. And so up to a point x, we're going to do that where x is y to the u. And because this is less than k times logarithm of p over the prime powers, this is essentially asymptotic to x. So at least as things go to infinity, this looks like 1 plus a very small error term. So at most. So essentially this average over primes is no more than 1, but it might be, if you're doing a random multiplicative function, you expect this to be tiny. And the maximum things can get in my example is if f of n is less than or equal, well, it's always less than or equal to the kth divisor function because of the definition. We know an asymptotic for the kth divisor function. So what I'm going to be interested in is the interaction between the average on the primes and, if you like, the average, the mean value of the multiplicative function. And we're going to divide by the maximum value so that, again, we've got something that's less than 1 asymptotically. So we're going to compare those two. And just using the standard sort of identity like this, we find if we pick the nth coefficient of a Dirichlet series, we get the following identity. We can sum that up to x. I'm going quite fast, so I hope you've seen this sort of thing before for the room zeta function. Well, here's all the, up to here is information on the last slide. We've got these 2 definitions. They're both less than 1 in absolute value because of the range I put lambda fn in, or f of it in. Here's this identity summed over the integers up to x. And then when I put it like that, I'm just going to use partial summation. So what I'm going to do is sum this thing, which I'll just use that identity. Here, d, the sum of fa. So this is just by partial summation. And then, well, okay, you've got to work with this a little bit and find out what the main term is. But the whole point of this exercise would look terribly complicated, but it leads you to something quite pretty. So the mean value, or at least mean compared to the maximum it could be, of f of n, in terms of what happens on the primes, you get yourself a very nice looking integral delay equation. So that opens up a whole lot of possibilities of techniques. And there's some error term, but one can throw that away because if you work with this and prove theorems, then you can translate back to the number theory world. So this is work Sound and I originated 25 years ago or so. Not quite so generally, but it's not hard to go more general. And so this is just for k equals 1. Here on the previous slide, I had d of t to the k, because that weight of the L function, the multiplicative function was k. It can be of size up to k on primes. The most interesting case in the past, at least, has been where it's inside the unit circle, the multiplicative function, so k would be 1. Sorry, I'm going the wrong direction here. So we get this much simpler looking equation. And one thing I'll just note is that you can take the Laplace, you multiply through by u over here, multiply by e to the minus su, integrate over u, and you end up with an identity for Laplace transforms. And so what's sort of interesting here is you've got, well, the Laplace transform of this thing on the integers, L prime, again, minus L prime over L, gives you the Laplace transform for this thing on the prime. So you're looking, a bit like what happens with looking at integers and primes, various L functions involved. So I just want you to get a sense that it's natural to look in this way, that you see things that you're familiar with, although there's some other interpretation needed. And just a bit of the algebra of such integral delay equations, if I have this function chi for a multiplicative function f, well, if I start with two functions g plus h on the primes, so I'm going to have f of p is g of p plus h of p. Okay, that's just on the prime, sorry, I didn't write that correctly. Then chi of f will be chi of g plus chi of h. And what you can prove is then that, in fact, the mean value over the fn is the convolution of the mean values for g and h, not very hard. And so this will become useful in what I'm going to talk about. So in particular, I'm looking at multiplicative functions where on the primes are no bigger than k. So we have a lot of theory when multiplicative functions are inside the unit circle. So I'm just going to do something crude like divide by k. I'll just assume k is an integer for here. You can do something more technical when k is not an integer. And so what this means is that the mean value of the multiplicative function f is the kth convolution of the mean value of multiplicative functions g. Yeah? I thought you were working with multiplicative functions, but now you're summing them. I don't quite understand what you're asking. G plus h, you mean g convolve with h? So no, what I'm saying is on the primes, I should have said this is on the primes. So f of p is g of p plus h of p just on primes. So I'm going to then create a multiplicative function out of that, yeah. So, okay, so here's some probability theory for you. So to understand what happens when multiplicative functions might be allowed to get large, of size of absolute value up to k, we have some convolution of what happens on for multiplicative functions that live inside the unit circle. And we want to get some idea of the size of this. And it turns out one of the better ways to proceed is to sort of understand where the main weight of this integral comes from, where are most of the terms packed in. And most of them concentrate around u over k. In fact, in some of the proofs I'm not going to give today, what we need to know is sort of what proportion are very close to u over k. Some of them are u over k times a logarithm away. Those of you in probability know this sort of stuff very well, I'm sure. So yeah, so I mean, it's sort of interesting. The only way we could really find in certain cases, to understand this integral is really to break it down into where most of the weight is in this sort of probabilistic way. I mean, you can sort of interpret an integral as some sort of probability over ti's between 0 and u, and then with this sum, and then you want to see where the weight is. Okay, so let me just give a favorite example of L functions and of multiplicative functions in number theory. Liouville's function, which is -1 on every prime. And one can show that the prime number theorem is equivalent to that the mean value of a Liouville function tends to 0. And the sort of counterpositive of that is that if the prime number theorem doesn't hold, that would mean the mean value of the Liouville function is not 0, as we take the mean for x up to infinity. And in a minute we want to interpret that. I should also note that you can express the Riemann hypothesis in these terms. I don't think there's not much useful work being done on that sort of thing, but it's worth noting. Okay, so up here we've got this question of the mean value of lambda n doesn't go to 0, so we need to know what multiplicative functions don't have mean 0? And there's an obvious class of examples, which is if you look at n to the it, right, that's multiplicative, and you take the mean, then it's more or less the integral of u to the it, and that's obviously x to the 1 plus it over 1 plus it, so you get this mean value. And it's kind of an interesting mean value because it's not tending to a limit as x goes to infinity. The absolute value is the absolute value 1 over the absolute value of 1 plus it, but it's actually spinning around the circle as x grows. Okay, and one can ask if there are any other examples, but the famous theorem of Halasz from 1968 is that if a mean value is non-zero, then of a multiplicative function f, then f of n is going to be close to some n to the it. And Halasz came up with a very interesting way to formulate that. And this is a generalization to multiplicative functions that are bounded by k at the primes. So there's been various versions before recent paper with Adam and Sound. But those are, well, let's just look at the k equals 1 case. This would be 1 over x times some n less than equal to x of f of n. So the mean value of the multiplicative function is bounded by something where if L gets larger, this is smaller and smaller. And what is L? Well, if k equals 1, we're taking, well, it's a bit strange. We're going to take t's up to log x, and then we can take 1 minus somehow a distance. Well, okay, if it's 1, when is this small? It's when the real part of f of p, p to the minus it, is near 1. But f of p, p to the minus it is in the unit circle. So it says something like fp is very close to p to the it. So this can only be small if the multiplicative function is mostly very near p to the it. And if it was k as the bound, it would be f of p is very near k times p to the it. It's the only way it could be small. So yeah, that's basically what I'm saying. So if this mean value was bigger than x over log x to the k plus 1, sorry, the sum, so the mean value is greater than a constant, then this would have to be less than 1. And yeah, so one wants to think about that a little bit. But if, for instance, I'm going to take, no, I meant to write, sorry, the real, no, maybe I didn't mean to write this. So let's just say you take minus k and k as the possible values of your multiplicative function at the primes. Then the only way, so you're thinking of k, and here it could be minus k or plus k. And so how could this remain consistently small if p to the it is going around the unit circle? So this would be plus or minus k times p to the minus it. Well, the only way it could be consistently small is if t equals 0. So if I'm looking at something like this, the only way I could get something to happen is if f of p is mostly around k. And so we get this. And another interesting example is if I just take mth root subunity that's going to come into this talk. So if I've got a small sum like that, so that's sort of something that appears a lot, obviously, in number theory, character sums, and so forth. If I'm summing mth root over mth root subunity, then when can a character sum be quite large? Well, something like this is going to happen. Okay, that on the primes, it's got to be close to 1 almost all the time, and as a measure of almost all is that this must happen. So, okay, let me explain this a little bit better. So let me just take a function here that's, I don't want to say this. Okay, one thing that's a little off-putting is that you're minimizing over all sorts of possibilities here. And what I said was that if you've got a real valued function, the only way this could be small is if it was 0. Sorry, if t was 0. So in that case, what you'd be looking at is k minus f of p over p. So can I get a theorem like this, but now instead of having a minimum over range of t just with t equals 0? Because that should be probably close to what's optimal. And here's a theorem from 1991 that if I've got a real valued function, multiplicative function, between minus 1 and 1, so on the primes it's somewhere between minus 1 and 1, then you can get an upper bound. But what we had expected from the previous slide perhaps was c equals 1 here, when we went over the minimum over all t. But in fact, the best possible result is some constant that's defined in some complicated way. So this generalizes fairly easily, sort of as noted in previous work I said of Adam and Sound. And this less than now, so for each, I want to do it uniformly in k somehow. So this less than becomes a constant depending on k. This key constant here is obviously another constant depending on k, and if you sort of follow the same proof as in Hall-Tenenbaum, well, you get something. And it was a little unintuitive what you get, and recently we had the thought of looking in this particular example, so just taking a multiplicative function which on the primes is, if you like, the divisor function for the kth divisor function for the primes up to y, and 0 for larger primes. And I'm sorry, it's quite complicated slides, but so what we're going to look at is, so we've got 0 on all the primes greater than y, so what we want is the kth divisor function, oh, I wrote dk before, but it's the same thing, tau k. The kth divisor function on the integers up to x, all of whose prime factors are less than or equal to y. And I want to compare that with a complete sum. And so I can just think of it as everything minus those that have got a large prime factor. And this is worse because if something might have 2 prime factors bigger than y, so this is an inequality. And then I can just use the estimates we had before for the sum of tau kn, 1 over gamma k, x log x to the k minus 1, and get this. Partial summation gets this. It's all a bit meaningless formulas, but what you end up with is something like this. So if you look at the kth divisor function summed over the y-smooth numbers, it's asymptotically the same as over all integers when I make this cutoff even as much as u is k over log k. So somehow it says that as k is growing, what's happening, at least in this extreme case, of what's important is, well, it's not the large prime factors. They don't have a big influence on the size of this thing, which is a bit of a surprise. We didn't know that before. So if you just plug in my formula before, this one, then this example, so what happens is we're saying essentially you have, well, we had fp equals 0, fp equals k on the small primes up to y, and f of p is 0 on the large primes, so this would be k over p on the primes between y and x. And what that means is, in order for this inequality to be true, we need alpha k to be exponentially larger than k. So that's a very unsatisfactory situation. It's not clean. We don't know what the right result is. And it also, we've been told something here, which is that the large primes don't play as much of a role as one might think. So I guess I should put 2025 plus, but so what we have is an upper bound on this, and we do have a constant. Okay, minus 1 over 142 is just an accident of a lack of skill. We do have a uniform result, but what's interesting now is that you remove a primes between x to the 1 over k and x. So actually you can go in this argument, with more care further than k over log k all the way to k. So yeah, so now we have at least a uniform version of Halasz's theorem, which didn't exist before. And we can see it's actually necessary in many situations. I mean, this is tip of an iceberg kind of thing. Okay, so yeah, it's a bit technical. I'm sorry about that. The key idea in the proof was, as I said a little bit earlier, was to study the size of this using these integral delay equations, and then looking how to understand this integral at u over k. Because if you think I have x is y to the u, so the exponent on y is u over k here. So most of the business is happening around there. And that was what we needed to understand. Okay, so just a little, actually maybe I'm going to, no, let me define this. So Soundararajan at some point made this definition of the pretentious distance, and it was known, this sort of formula from Halasz's work. But defining in this way means it satisfies the triangular inequality, so it's reasonably easy to work with in many situations. So Halasz's theorem now appears in this form. And in 2009, we suggested that perhaps pretentious distance could replace Zeeman zeros in all the standard zeros in analytic number theory, and that ended up working out. I should say in our early work, we had failed to get results as strong as those from Riemann zeros, and Dimitris then showed how to get results as strong. And then subsequently, Adam showed how to give much nicer proofs than we gave, so that a lot of technicality disappeared. So we're able to prove, I think, more or less everything in Davenport fairly straightforwardly, including Hoheisel and Linux theorem. From pretentious methods, and of course, there's been a lot of use of pretentious methods over the last 10 or 15 years and going in directions that I don't think we could possibly visualize back then. Okay, so let me show you an early result that Sound and I worked on, and then I want to tell you about many general directions it suggests, some of which we've been working on. So we're going to work just with multiplicative functions that only take values in -1, 1. And we're going to ask, what are the possible, maybe I'll just go to that. What are the possible mean values of a multiplicative function that only takes values in -1, 1? So f of 1 is always 1. Okay, so there is a mean value 1 in there. F of 2 could be -1, so up to 2. You could get 1 plus -1 or 1 plus 1. At 4, obviously you've got another f of 4 is 1. But the interesting one is, let's sum all the way up to 6. So we know that f of 1 and f of 4 are 1. And then here's the interesting one, is that if f of 2 and f of 3 are both -1, then f of 6 is +1. Right? So we can't avoid having at least 3 1s up to 6. If a multiplicative function only takes value on plus or -1, you have to have 1, 4, and 1 of 2, 3, and 6 being a +1. So the question is, what's the minimal number of +1s you can have? Can you have less than half? So far, I haven't shown you an example where less than half of the integers up to x, f is +1. Maybe you can go below a half. Actually, it's easy because you can do f of 2 is -1, f of 3 is -1. But so what's the sort of minimum proportion that a +1? So let's suppose you had, so for the mean value, so suppose you had a quarter being +1, that would mean 3/4 were -1, which would mean the mean value, which is the ones minus the -1s, we'd have a mean value of -1/2. So the question really is, what is the lowest the mean value can be in the negative direction? And if a mean value is non-zero, then we can use Halasz's theorem, and it tells us something like this. So the obvious thing to think here is probably, well, we'll have t equals 0, and then we'll have 1 minus 1 a lot of the time. And in fact, it is the only way to go. And so we must just have that f of p is -1 on a relatively limited set of primes. And, well, this is sort of what I just said, that we suspect the mean values should be in some sort of interval. I gave you an example with 1, 2, and 3. And so it should be some sort of interval with the lower bound being between -1 and 0. And Hall proved that it's really inside that interval in 1996, the lower bound. So you can't get 100% -1s from multiplicative function out to x, but you can get more than half being -1s. And then the question was around for a while, what is that proportion? And there it is. So what we proved is that the smallest mean value of a multiplicative function just on plus and -1s is -0.656999, which is essentially a dilogarithm function. Okay, so what I want to do is explain a little bit where this comes from. Obviously, it's a bit meaningless as stated, just a number. So we proved a little more, which was that the only way you can get down there is that if your multiplicative function is 1 on the primes up to some point, and then it's -1 from there on. And when I say essentially, I mean that the distance between such a multiplicative function f and this is little o1. And that's sort of one of the origins of the word pretentious, that f pretends to be this g. And this g is that there's a sort of a multiplicatively constant interval up here between y and y to some power, which is 1 plus root e. Okay. So this is sort of a structure I want you to keep in mind. And the corollary is, well, if you look at the number of ones, right, if I want to count the number of ones, it's going to be 1 plus the mean value over 2. So So this will be the number of ones, and then by the law of quadratic reciprocity, you can prove this cute result that the proportion of integers which are quadratic residues mod p over all primes p as you go sufficiently large is always bigger than 17.15%. Okay, so that's our result for -1, 1. But what if instead each f of p is a cube root of unity? What can we do? Or a fourth root of unity. So I'm going to define sk from now on to be the set of kth roots of unity, and gamma k to be the set of mean values. So these are multiplicative functions f, and again, think of them as totally multiplicative, where the primes are in the kth roots of unity, but products of kth roots of unity are kth roots of unity. So every fn is a kth root of unity. So what happens when you take a mean value of a sum of kth roots of unity? It's going to be in the convex hull of the kth roots of unity. So what we have is this mean value over the values on the primes, and the mean value on over the integers are both going to be in the convex hull of the kth roots of unity. So what I should say is Soundararajan made some comments on this in 2001 in our long paper, and we obviously, trying to do square roots was trying to understand the possible mean values of multiplicative functions plus or minus 1 is going to be a line segment in the reals. Trying to understand the mean value for multiplicative functions on the cube roots of unity is going to be some region in the complex plane. So unless it's very convenient, this is bound to be difficult. And we sort of gave up at that point after making a couple of observations and conjectures which are mostly wrong, but for good reason. So we will study this using, again, this integral delay equation. Here the chi has absolute value less than or equal to 1, and thus sigma. Now, if you were into integral delay equations, I don't think we've spread the net quite that far here, but this is a typical Volterra equation that applied mathematicians use because what it's saying to an applied person is that what happens at time u is dependent on what happens in the past. So t is time. So here, the current situation is some sort of weighted average of the past situations. So they use this in brain modeling and all over the place. But here's the problem is that in applied mathematics, they typically have an idea of what chi looks like, and then they alter the starting conditions. Okay, so here, in our case, our starting conditions are fixed, and we're altering chi for t greater than 1. So we're doing the exact opposite of applied mathematicians, and I'd long ago realized these are Volterra equations and talked to applied mathematicians who basically said, you can't do anything. You can't with these sorts of equations. I should say, this also comes into sieve theory. I mean, a lot of sieving is really, when you use a sieve identity, you're essentially saying what happens at a certain height in terms of earlier heights. So you see this sort of structure in some Montgomery's work, for instance, on sieves. So the main software for doing Volterra equations is MATLAB, and it's not suited. And I'd accepted that fate for a very long time. And then I happened to be on a committee for postdocs in Montreal for our most prestigious postdoc. Actually, the Clay postdoc, not science. But anyway, so it was a general across all of mathematics, and there was an applied mathematician applying, and all his letter says, he does miracles of MATLAB that nobody else can do. So I thought, maybe when we should pick him as one of our postdocs, but the applied mathematicians had said he was the #1 choice. And then maybe I should ask him if he can make MATLAB work for analytic number theory. So Kevin came to Montreal, and we've been working for quite a while now. So here's one of many pictures that he's drawn for me. And I should say, it took a long time to get to this neat picture because how do you model something in 2 dimensions like this was really hard. Until you find out how to do it, and then it sort of sounds really easy. So again, we're going to look at the mean value multiplicative functions that are defined only on cube roots of unity. And the mean values must be inside the convex hull of the cube roots of unity. So I've drawn the unit circle and in red is the boundary of a convex hull for the cube roots of unity. And then it turns out all the mean values are inside exactly this picture we got. Now, I'll show you in a little bit how we define this curve, and it's an induced definition, so I don't know a simple way to define it. Sound and I had proved, actually, that this region must be star-like. So if you have some point, then that point joined to the center of the circle must be in all mean values. So we do know this is the correct region, more or less. So here we are for fourth roots of unity. And what you can see is it's pretty much crowding out the whole thing, but it doesn't reach these. Well, if you think about it, it's never going to be I, the mean value. I mean, if the mean value of multiplicative function was I, it would basically mean every f of n was I. But if f of p and f of q are I, then f of pq is -1. Right? So it's going to be difficult to be right up there. But it gets close. OK, I could go on and on with pictures. We had fun. Once we figured out how to do this, we can almost prove these are the correct curves, but well, hopefully at some point we will. Let's put it that way. So how do we understand this boundary? Because what's important for us is what's obviously the boundary of what we call the small Sound and I call the spectrum of mean values.
So Andrew,
yeah.
The black circle touches.
Yes, it touches here, just here. So the mean that's actually turns out to be straightforward, that bit. But yes, it does touch. It's not an accident.
Can you prove the excluded volume tends to 0?
Yes. Yeah. I mean, it does try and fill in the gaps. Yeah. Huh?
As k tends to infinity, the number.
Yeah, exactly. Yeah. Yeah, this works for all x large, but just not for x small. Yeah, I didn't say that very well about where the cutoff is, but once x is large, yeah, the asymptotics come in.
You have to change your function.
No, but then, yeah, a single function.
So what I'm talking about is these are mean values at large x for a single function. Okay, so for each possible function at x is a gazillion, we write down all the mean values and it'll be dense in this region.
Yes.
Yeah. Okay, sorry, I didn't quite understand.
If you take a fixed function, you take x to infinity. This gives you.
Oh, that's a completely different world. That's a completely different world because it'll either go to 0 or to an Euler product. So it's much easier, that family of questions. Yeah. Yeah. Okay, so what I'm going to do is instead of trying to understand everything in the region, I'm just going to try and understand the boundary. And here's the problem is I don't know how to do that in a sort of a one-dimensional way because it's a two-dimensional object. So we finally hit upon an idea of how to think about the boundary, which is, well, let me go back. So you can see here e to the I theta times the mean value, minus I theta. So here's the thought we had. Oops, sorry. Yeah, go back to. Is if I want to find out what's happening over here, what I could say is, well, let's just take a direction and then find the furthest. I mean, if we sort of draw a perpendicular line, what's the furthest anything is in a certain direction? So what I'm going to do is take e to the minus I theta times everything on here and look at the maximum real part of that. Okay? So that allows me to have an infinite set of one-dimensional questions, which I have tools for, turns out. So it's simply this that I'm looking at. What's the maximum over all multiplicative functions f, where x is very, very large? And here's the idea, is if I take a prime, the main contribution is going to be where the prime divides the first power. I mean, not a prime that's too small. So the main contribution will be f of p times the sum of f of m up to x over p. And if you like, the p squared, the contribution will be no bigger than x over p squared, so small. And then what is this? Well, in terms of what I've said so far, this thing is x over p times the sigma function, sigma u minus it. And so essentially what I'm now looking for is how to maximize the real part of this. And I want something that's optimal. And so if it's optimal, let's just suppose we have an optimal function. So sigma is optimal. Then I'm going to want to make this real part as big as possible. So I'm going to have to choose f of p so that this is optimal. Now remember, f of p is a k-through-tube unity. So what I'm going to want is f of p to try and get close to this times this times this to point as well as possible in the positive real direction. So as best possible, I want f of p to look like e to the I theta times the conjugate of this. So essentially, it's going to be the k-through-tube unity nearest to this, up to small error terms. Now, sigma is defined by an integral, so it's continuous. So I've got some function that's moving here, and I'm looking at these f of p's, and p is at y to t, so that's why I put chi t there. And these chi t's are discrete. This is continuous. And it's the discrete k-through-tube unity nearest something that's moving continuously. So what this means is this is bound to be fixed on intervals, right? Think about it. Something's moving continuously. I want the nearest k-through-tube unity. Then, it sort of gets to in between, and then I hop to the next k-through-tube unity. So sigma is continuous by construction. Chi must be fixed on short intervals, and it must look something like this. And so it means we could actually compute and try and find optimal examples. And then the question was, where do you cut up the intervals? Where are the t1s, t2s, et cetera? The first interesting cutting point is 1 plus root e, which is what we saw in the work of sound. And, well, anyway, it's a long, complicated story of how we find these things. So we're still in the process, but we've made some progress, as you can see. So what's strange is I'm not 100% sure I understand this, because we know all these, and that's what I drew, is the maximum in every direction. Haven't entirely proved that that's the maximal area. There could be something non-convex on the boundary. I just don't know. We haven't found any examples, so I'm sure there isn't, but who knows? Okay, so let me move on to another question, which is I said before that with the quadratic case, I was looking at the least number of quadratic residues. And I could ask that with kth power residues. So if I make the Fn being kth roots of unity, what's the least number of ones? And then what I said before is it was a half of 1 plus the mean value of the multiplicative function. But if you try and imitate that even with cube roots of unity, then you're going to, that should be to k minus 1, but you're going to be summing over k mean values here to do this. And they're not independent. So it's actually tricky as k grows. So for instance, k equals 3. We're going to have to deal with this. This isn't actually so bad if k equals 3 because f and f squared are conjugate of one another because they're cube roots of unity. So if k equals 3, it's sort of within the realm of what we've already done. But already for k equals 4, it isn't. So what I should say is we can come up with examples where we get 1, which is quite small. The number is quite small. And the way we do it is we just have f of p be 1 for all the primes up to x to the 1 over k, and f of p be a fixed kth root of unity for all the bigger primes. And if you think about it, to get a multiple of these getting 1, we'd have to have k of them multiplied together, but each prime is bigger than x to the 1 over k, so you won't get that by x. So the only f of n that equal 1 are products of the small primes. So it's going to be the smooth numbers. It's a well-known function for analytic number theorists. There's this probability that an integer has all its prime factors less than x to the 1 over k. It's the Dickman-de Bruijn function rho of k. And most importantly for us, it looks like k to the minus k. So it's quite interesting. You get an amazingly small proportion here. I mean, so if k is 100, this is already 100 to the minus 100 of the things are 100th powers, which is way small. So this is a sort of trivial construction. And then the question is, what's the right answer? The only thing we did in 2001 was able to show in a logarithmic version we got a quite neat lower bound, which is sort of a different flavor to this. So I visited Kaisa Matomäki in Finland a couple of years ago, and we were able to get some results on the kth roots of unity. So in this logarithmic question, so you're just looking at, well, you all know about logarithmic weight as opposed to natural weight. Questions tend to be easier. So we thought we'd start with that because it was too hard to do natural density at first. And we were able to get this number being this thing, more or less. So it looks a bit like something you get out of Stirling's formula to the 1 over E. It's not incredibly meaningful. But what's interesting is that you can only get a sum, an f of n, where the number of ones is this small logarithmic measure if it looks like the example I just gave you. And the question is just, where's the cutoff? Okay, so it's got to be 1 and then zeta k. And again, it's sort of pretentiousness, it looks like. More interesting is that, let me just skip that statement, is we then were able to make some progress on the natural density. And I said to you that trivial example gave rho of k, which is a very different flavor from the thing I just showed you. What we were able to show is that the minimum proportion, at least as k goes to infinity, beats that by some constant to the k. And this constant is this mess. And again, we're able to prove that the only way you can get a small proportion. So in my theorem of sound, we did this sort of thing, and it was y and y to the 1 plus root e for square roots of unity. For kth roots of unity, it's going to be the same, that the function looks like 1 and a primitive kth roots of unity, y to the something a little bit bigger than k is going to be the right way to do it. It's actually quite hard to pin this thing down, but we haven't succeeded yet. Okay, so that's an old question where we've made quite a lot of progress. Haven't quite nailed all the details, and I think we're probably going to publish before we do, and up to somebody else to get exactly the right results. And there's something neat to be got. Okay, so I want to tell you about the LSD theorem. So a piece of advice, if you need a lot of links, a lot of downloads of your paper for your promotion, call your paper something like the LSD theorem. The Landau-Selberg-Delange theorem is what I'm talking about. But just for fun, Demetrius and I called our paper this, and we've had thousands of downloads. We're on medical websites, all sorts of things. Okay, so Selberg's great result is that if you have a multiplicative function that's defined as the alpha power of a zeta function, here alpha is not necessarily an integer, then the mean value of f of n looks like, strangely, log x to the alpha minus 1 over the gamma function. Yeah, and this only makes sense if alpha's not a negative integer, because if it is, 1 over gamma would be 0. Okay, so it would be a little trickier. And so for alpha equals 0, we just get, well, the function is 0, so that's not very interesting. But if alpha is minus 1, then we get the function lambda and the Liouville function. And that's related to the Riemann hypothesis, and that the size should be about x to the half. Okay, so Delange in 1959 extended, so I should say, well, I'll say in a minute what Landau did. So Delange in 1959 extended this to multiplicative functions that are alpha on average in some very formal way. In other words, zeta functions were involved, and then Demetrius and I tried to sort of remove a zeta from this and say alpha in a more less restrictive way, the averaging. So Landau actually worked this out for a very similar proof to Selberg, just for the case of sum of two squares, because integers are the sum of two squares. Well, you know what the structure is. All their prime factors are 2 or 1 mod 4, or squares of primes that are 3 mod 4. And so you basically get zeta s to the half times something. So that's sort of in the nature of what Delange did. And so Landau and actually then Ramanujan were able to prove just the case alpha equals a half, and then some constant, as in Delange. Well, I just gave a sort of general constant there for the case of a half. Okay, so let me talk a little bit about how Selberg did this. So we're just going to use Perron's method. So we want to find coefficients of this thing. So we're going to integrate along a line to the right of 1. We'll truncate at some point, and the usual x to the s over s ds. And so what Selberg did was he pulled the contour back, and all the dotted lines are easy enough to deal with. But there is this partial pole of zeta. Well, zeta obviously has a pole at s equals 1, but when you put it to the alpha, it's just weird. So you can't really include that in the region, so you've got to put something around it, and that needs to be understood, that contour. And then the idea is to resize, and the obvious resizing is, well, I mean, we're going to have S equals 1 plus something as we go around this, and the correct scaling is C over log X. So if we do this rescaling, then the integrand, and pole at S equals 1 gives us that, and then you can just work out, you get something rather nice. The log X powers come out, and you just get Z minus alpha e to the Z. And so you now get this integral, you just extend it to infinity, and lo and behold, you've got Hankel's keyhole contour. So it all works out very nicely. That's basically the proof, though the details are a bit challenging. So one thing I've long been really interested in, and we're finally getting some more work on this, is, well, you've seen these in these examples, but there's not been a lot of theory on them. Two-tone multiplicative functions, as I call them. They're not just alpha forever, they're alpha, and then they change to beta. So it might be 1 turns to 0, 3 turns to -5, but it'd be nice to have a theory of these things. So what the Landau-Selberg-Delange theorem gives is that if I look at sort of the mean value for this thing, then I know it when I'm just going up to this point, because it's just alpha, and that was Selberg's theorem. And I know it as u goes to infinity from Delange's contribution, but I don't know the transition in between. And actually, there's been some work back in the day with Hafner, McCurley, and Goldstein trying to do this in certain sieving situations, trying to understand these transitions, and they're quite hard to understand. So things that are known are functions that start as 1 and then 0, the smooth numbers, and then you get a decay that's 1 over u to u. It doesn't look like 1 over gamma, right? 1 over u to u, because that gamma thing was, well, you can see it here. It's u to a power over gamma. There's sieving ones. And then the work I did with sound, we got a little bit of information where you go from 1 to -1, but actually fairly limited information. We just found the global minimum. That's what we worked on. So I'm just going to work with real numbers, positive real numbers, and I'm going to start it as being plus, and I'm going to then move to minus a real number. And again, I know what happens when u is less than 1. Well, that integral delay equation I gave you at the start, in this case, when you differentiate it, and you multiply through by the right kernel, then you actually get a rather nice differential delay equation that you can work with. Whatever, it's a technicality, but it's a useful one. So I know what happens as we go to infinity for the mean value. I know what happens when u is less than 1. I want to work out the transition, and I have this tool to work with. So let me go back to, I'm going to create another tool, which is how do we do the generalization of Selberg, because that's the obvious thing to do. I mean, Selberg did it for just a fixed value, so maybe we can imitate Selberg for 2 tones. So essentially, for infinitely many primes, it's going to be minus L. So it's obvious to put in a zeta S to the minus L, and then put in a correction factor for the small primes. And so this is just the Riemann zeta function up to y. So we do basically the same integral, and we're going to what we did essentially in Selberg was understand the size of this function. And so it would give us the mean value, it would be the integral of e to the something. And again, I'm going to change my parameter s as 1 plus z over log y. And here, remember, I started with k and went to minus L, so it turns out m is k plus L is the natural parameter. And then this thing is more or less this thing. Okay, so a bit like in Selberg, remember you went to e to the minus z, z to the k. Equally, in this world, you go to something that looks considerably simpler than the number theory, let's put it that way, with a small error term. So what we want to do is try and push the region of integration to the left. We've got some really weird and screwed up values. Well, not quite poles, they're weird powers of poles. We've got this zeta function that's not the best behaved thing in the world. And we need to understand what's going on. First thing to understand, because we're going to use the saddle point method, is to understand where the saddle points are. So when I take the derivative, it turns out to be nice and simple. This has infinitely many zeros, infinitely many z, but they tend to start splattering well away from the real axis, and it turns out the ones near the real axis are the ones that contribute. So, okay, it's a bit technical, but let me just say when u is small, we get what we started with times something that starts to decay at some point. There's an intermediate region. Okay, actually, I've really put these slides in the wrong order. So I'm going to go forward a bit and then come back to this. Okay, so this is let me start with the interesting one, okay? The most interesting one a priori. So what I said was that, well, even in the case with Selberg, you have, when you're looking at L not an integer, you get something over gamma to the minus L. And when L is an integer, you get something different, which in that case, we just went to something like the Liouville function. So it turns out in this generality that something very different happens in this case, where you've got these two-tone functions. So if L is, well, okay, let's interpret this. So if L is, so this has a row function, so it dies like e to the minus u log u. And this dies like a power of u. So this dies much, much slower. So as long as this coefficient is non-zero, this is going to dominate over this. So the first term dominates unless L is an integer. And when L is an integer, this guy dominates because this thing's zero. And so here we have, well, it's reflected in the few results we already knew, that if L is not an integer, so remember it's k and then minus L, the value of the primes, it'll decay like a polynomial. And if L is an integer, it'll decay a bit like the Dickmann-de Bruijn function. So this is the new contour of integration. So we have something very similar to Selberg's point. And then there turns out to be a second one. So there were two main terms there, right? And they're both on the real axis. And what happens is, well, it turns out because of the way the saddle point is, you need to go in that direction to pick up the residue. It's rather odd. It's a little bit different. Yeah. So what I wanted to, I'm not doing so well for time, I guess. And then we're quite interested, well, let me not say anything about that yet. So, okay, so we have these two saddle points, and here, as u gets large, they're both real, and so we're able to do something with them. But when u is a little bit smaller, let me go back, the range I missed, we actually get two conjugate. We get no real saddle points. We only get imaginary, complex ones. And so the two lowest height ones combine, but then we find we get a cosine in there. And a cosine means oscillation. So what does this all mean? Okay, I wish I put these slides in a slightly different order, but anyway, we have what we have. So what does this all mean? Well, let me show you a graph of what Sound and I worked on years ago, which is f of p is 1 for the primes up to y and minus 1 after that. Now I'm just going to look at the mean value, okay, the mean value of f of n, given that these are the values of f. And it starts at 1. It goes shooting down to this value that we found. And then it comes up again and monotonically tends to 0. It hits 0 once. Never again goes positive, this thing. But it does seem to be converging very rapidly, and in fact, it converges like rho. So here I'm going to take k equals 1.5. And again, it starts at 1. It comes down. It crosses the axis again. And then it monotonically goes to 0. And if I do k equals 2, it's also got two zeros and has very similar behavior, though in fact you can't see it unless your eyesight's much better than mine. But this converges much faster than this to 0. Here's 3. And 3, we get 3 zeros. And 5, we get 5 zeros. So thanks to Kevin being able to compute, we discovered that the number of zeros of the mean value is the smallest integer greater than or equal to k. And then we got that cosine formula, which said there are oscillations. And, so here's 5.5, we got 6 zeros, and 6, we got 6, well, you get the point. So then they're roughly equally spaced. Then using that cosine formula, we were able to show that's the right number of zeros. We're able to show this decay if k is not an integer and k is an integer. The global minimum, I don't think we've quite proved that, but I think hopefully we are going to prove that. That, well, you can see on the graph it's obvious, but in practice it's not so easy to prove. That the global minimum always occurs at the first. It should decay like exponential in k. Yeah, prove these statements more or less. Okay, that's it.
Questions for Andrew?
I blasted you with many papers, which makes it hard. Yeah.
Can you imagine doing two-terms function? Like you had a three-terms function, four-terms,
Pierre, it's for you. Now, I mean, we've made quite a lot of progress here. There's a lot still to understand to feel like we have all the analogies to what we know about the one-term functions.
the two-terms, you had two poles, right? So you expect more and more.
Oh, I have no idea. Not thought about it. I don't even really know how to formulate it very well, to be honest. And once you get into the proof, there's going to be new issues that we haven't addressed, for sure. Yeah. So a lot of this actually, we tortured ourselves with this. I mean, I've drawn a graph there, right? If I've got complex numbers, it's not so easy to draw, and it's not so easy to interpret what the analogies are. So it's clear a lot of the methods go through, but it's not clear what the interpretation is, even if they do. But obviously it's the thing. So I think instead of going for 3, like Louis Pierre suggested, I prefer to go next to go to the complex stuff and to try and understand what on earth's going on with that. Yeah. Oh.
On the minimum number plus ones, where you have a case of unity, can you show that the optimal example is of the form union of intervals? This result you have with
Yeah.
you can numerically optimize.
No, okay, so I've gone through many things. So with Church, we were trying to get the whole spectrum. With Kaisa, we were just trying to find some minimal stuff. And there, it's just 1 and then a root of unity. The one with Church, we do know it has to be a set of intervals for the optimal in any given direction, but we don't know exactly what they are. Yeah. You can define them in terms of solution to a bunch of differential equations, but I mean, it's very induced. Yeah. Did you have a question? Sorry. No. Oh, down here.
You mentioned when you were trying to optimize, right, convex healthy average of the multiplicative functions, that it was different. It wasn't just one fixed multiplicative function, because that conversion would have put that.
Right.
Can you say anything about what causes f of 2 or the value of fixed function to change in the optimal?
To change. I don't quite understand. So if you fix the multiplicative function, then at some point either you're going to have so many f of p's that are not close to 1 that it's going to go to 0, or you don't, in which case it's going to converge.
So if you look at the optimal one, it must change, and so the value of a fixed prime must change, f of 2 must change in the optimal.
F of g, I'm sorry, I'm not quite understanding.
If you look at the thing that's optimizing the function at a fixed x,
Uh-huh.
the value at a fixed prime must change.
Yeah.
Can you say anything about what causes the change?
Solution to differential equations. No, I mean, we'd like to have a natural interpretation. So actually, 30 years ago, well, when Sound and I did that 1 and 1 plus root e and got that strange constant, I talked about it at Princeton, and Conway got very obsessed by the constant, which is sort of his thing. And he was like, how can you live without interpreting this? So, but we still haven't got a very good interpretation. It's just, it comes out. Yeah. So, I'm sorry to disappoint you too.
Maybe one last question?
Do you have something to meet? Oh, over there, Adam. Yes. No, we didn't think about that. No, it was, The contracting issue is a different issue, I think. I don't know. Have you thought about that? I mean, obviously a half is an interesting thing for set theory reasons, and probably worth thinking about, but I haven't done it. Did you have something?
Yeah, so this sine term, you have two terms in
Yeah.
asymptotic. This comes from the line? Or the two
Yes,
lines?
yes, yes, yes.
But there is a change of argument there, so it's not really a line, right? You have to treat them as two lines. My question is there a change of argument on your...
I think you've probably made a very good point, but let's... Yeah, yes.
So when you actually calculate these terms as
This guy, yeah.
when you go over that line, there's probably discontinuity in your integral.
Well, yeah, you're going to compute there and you're going to compute there, essentially.
You add them up.
Yeah, you add them up, and there's some cancellation, so you get to a sign. Yeah. I mean, it's two complex things. I mean, essentially, they're both the same thing. By the way, I originally presented, instead of having gamma L sine pi L over pi, I put over gamma minus L, but I find putting sine and cosine makes it a little easier somehow. Maybe not. I mean, there's these identities for the gamma function you can use to present it differently.
Okay, there is a lot of interest, but I suggest we postpone more questions for lunchtime, which is now. We will resume at 1, and thank you very much, Andrew, again, for a beautiful talk.